In probability, it's important that we're able to count the number of ways that things could happen. And so today's lesson is about trees and counting techniques, and this first one is called tree diagram. If you were going to make a schedule for yourself and you had to choose one of these period 1, one period 2, and one of these period 3 classes, how many different schedules would be possible? One way to count that is by making a tree diagram. So we could first decide, okay, well, there's 3 different ways we could choose our period 1 class. We could choose leisure sports, U.S. history, or French. And then if we choose leisure sports, then our second period class could be trig or chemistry. If we chose U.S. history, it could be trig or chemistry. French, then we could choose trig or chemistry. Then once we've got our second period class chosen, then our third period class could be chosen. Period 3 is accounting, biology, and economics. So, for example, if we looked at this A right here, that would stand for the event of choosing U.S. history for first period, then trig for second period, and accounting for third period. And so if we wanted to count how many different schedules there were, we could just count how many different final branches there were in the tree. And it comes out to 18 different schedules. The multiplication rule is just a shortcut to figure out how many different schedules there are. It says that if there are 3 choices for period 1, 2 choices for period 2, and 3 for period 3, we can just multiply each of those, and that would also tell us the number of different outcomes for how many schedules there would be. The multiplication rule makes it so that we probably wouldn't want to make a tree diagram usually, but if we add probability to that, it might make it a little more useful. Let me show you how we will figure out the probability of grabbing a snack and then another snack. Our snack basket has 5 fruit snacks, 2 granola bars, and 4 bananas. And so the probability of grabbing a fruit snack, how many snacks are there? 11 snacks. And 5 are fruit snacks. 2 are granola bars. And 4 are bananas. So that gives us our probability for grabbing our first snack. Now for grabbing the second snack, these are going to be dependent events. And so if we were to grab another fruit snack, we know that that probability is going to change because there are no longer 11 snacks in the basket, there are now 10 snacks in the basket. There used to be 5 fruit snacks, but now there's only 4. So for each of these second draws, there will only be 10 snacks in the basket because we've given that we've already taken a snack out. And then, for example, this one, the probability that we grab a granola bar, given that we already took a fruit snack, that would leave 2 granola bars, that would leave 4 bananas. Given that we've already taken a granola bar, we would still have 5 fruit snacks, only 1 granola bar, but 4 bananas. And given that we've already taken a banana, that would leave us with 5 fruit snacks, 2 granola bars, but only 3 bananas. Then we know that the word and means multiply. So I'll take the 5/11ths times the 4/10ths, and I'll get 20 over 110. For the probability of fruit snack and then a granola bar, we'll take the 5/11ths times the 2/10ths. And then we continue that process, taking the probability of each event times the probability of the second event given that the first event happened, and we get our final outcomes probability. A great way to check to see if you've done everything right is to see what the sum of all of those probabilities are. Since that represents the entire sample space, we should get 110 out of 110. That should be 100% of the possibilities. Here's one where we would definitely not want to make a tree diagram, so we're going to try to use that multiplication rule. An area code like 701 was originally designed as a 3-digit number where the first number was a number from 2 to 9, the second digit was a 0 or a 1, and the last digit could be any number 0 through 9. How many area codes are possible using these constraints? So my favorite way to figure this out is just to sort of make a spot for each digit and then decide how many possibilities there are for each spot. And so if the first digit is a number from 2 to 9, how many numbers is that? It's actually 8 different numbers. Count it on your fingers if you don't believe me. The second digit is either a 0 or a 1, so there are 2 choices for a second slot. And the last digit could be any of those numbers, so that's 10 choices. And if we multiply each of those, we get 160 possible area codes. Of course, we wouldn't want to use 911 as an area code or 411. All those 811, 211s are all reserved for special services. So what if we had to reserve those? Then how many possibilities would there be? Let's figure it out. Let's try counting how many blank 1-1s there are. So if this is a 1 and this is a 1, that would leave us with 8 choices here, only 1 choice here, and only 1 choice here. So it turns out that there's 8 of those in the form of something like blank 1-1. And so then that would leave us with only 152 area codes left. Ava, Becky, Carol, Debbie, Emily, and Faye need to be seated on a bench. How many ways are there to arrange them? So we have A, B, C, D, E, F, and we need to put them on a bench. Let's do that same sort of technique where we make those 6 spots on the bench. And then we just decide how many choices do we have. For this first spot, there are 6 ladies, so we would have 6 choices for the first one. Now that somebody's already sitting there, how many choices do we have for the next spot? We would have only 5 people left to choose from. And now that 2 people are sitting down, we'd be down to 4 people for this spot. Then 3, then 2, and finally once we get to that last one, there's only 1 person left, so that 1 person is the only person that could sit there. So we'll take 6 times 5 times 4 times 3 times 2 times 1, and that's 720 ways. You might remember that 6 times 5 times 4 times 3 times 2 times 1 is also known as 6 factorial. Factorial just means taking that number and taking that number, subtracting 1, subtracting 2, and keep on subtracting, 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 and multiplying till you get down to 1. By the way, 0 factorial is defined to be 1 because we can arrange 0 things in one way by not arranging them at all, and 1 factorial is 1, kind of like you'd expect. Here's a special case. How many ways can you arrange the ladies if Emily is not allowed to sit on an end? Maybe she's a troublemaker. Then we can't just use a simple factorial. So I like to go back to my box method. Since those end spots are special, why don't we fill those first? For this first end spot, I can't use Emily, so I'd only have 5 choices for this end. And once I've used somebody on that end, I would only have 4 people left to fill that other end in. Now that I've got 2 people on the end that are not Emily, now I can bring Emily back into the mix and I can decide who's going to sit in those middle 4 spots. Out of the 6 people, I would still have 4 left, so I could put 4 people here. Now that one's sitting, so I'd have 3 left, then 2 left, and finally I'd fill that one last. And that comes out to 480. So I'd encourage you to try this little box method. Make those boxes and try to figure out how many choices you have for each box, and then use the multiplication rule to count up the number of ways.